So in continuation with the graph theory basics, the next topic we will cover is the minimum spanning tree. Okay. So the main idea or the plan for this lecture is, instead of directly defining the problem and giving an algorithm for its solution, so we will first see an application which actually requires this solution, and we will do a backtrack to what is a minimum spanning tree and what is the algorithm to do it. Okay. So in the previous lecture, we have seen, given a graph, how to represent it in a computer. Okay. So we have seen how to represent using an adjacency matrix and an adjacency list. Okay. So for now, let's take a common example for this lecture and consider this graph. Okay. So imagine we have a country and there are some cities, and we want to connect these cities using some roads. Okay. So the vertices represent the cities and the edges represent the roads. So A, B, C, D, E, F, G. So there are 7 cities in this country, and consider this problem. So the government of the country wants to connect these cities so that there is a road from every possible pair of the cities. Okay. So and the edges here actually represent the roads which can be built. So let's say to build this road between the cities A and B, it costs 7 units. Okay. So similarly, I will fill the rest of the details. Okay. So as you can see that each edge, along with the information it connects two vertices, it also has information about the weight. Okay. So it is a weighted graph, and also we were not associating any sense of direction to it. So we will consider undirected and weighted graphs. Okay. So on the weights we are giving here is on the edges. Okay. So the problem definition is finally, so there are some cities and there are some possible plan for the roads to be constructed. Okay. So we can, if we construct a road from A to B, it costs us 7 units. Okay. So similarly the rest of the edges. Now the problem is, the government should plan to construct some set of these roads such that every pair of cities must be connected by a road, by a path. Okay. So let's take for example, so the blue edges are the ones which can be constructed, and the actual roads that are constructed, I will mark them using the red color. Okay. So let's say we construct the road and it costs us 9 units. Okay. So we construct this road. So let's just take some random example. So we have selected some edges which are represented using the red color, and if we start from any vertex using only the red colored edges, you can reach any other vertex. Okay. So that's what is meant by connectedness. Okay. So using edges, using only the selected edges which are represented in red color, you should be able to find a path between any pair of vertices. So that property should be satisfied. And what is so we can actually select some random edges and actually get the graph connected. Okay, so but what is the main problem here? So the government tries to reduce the actual cost it takes to build all the roads. Okay, so if we consider this particular instance of the solution, so we are selecting this edge, so the cost will be 7 plus 9 plus 8 for this edge plus 7 for this edge and 8 plus 9. Okay, so this is the cost that is incurred if we select this red edges. Okay, so now the problem is select some edges such that the sum of the weights are minimized, and you also have to make sure that any two vertices are connected using by following only that set of edges. Okay. Yeah. So let's add. So there is a missing weight on this edge, so it is 15 actually. So let's define the terms which are in the problem. Okay. So let's go back to the original graph in which we have the roads yet to be constructed, and we need to select some set of edges from this side. Okay. So this is the original graph. Okay. So what we want to select is a subgraph. Okay. So we need to select. So this is the graph G given, okay, and we need to select some edges, so we can treat that as a subgraph. Okay. So this is the notation for representing the subgraph of a graph. Okay. So G prime is a subgraph of G, so this is what we need to find. Okay. And the properties for G dash should be, it should be a subgraph of G and it should cover all the vertices present in the graph. Okay. So in graph theory terms, it is also called as span. Okay. So if G dash contains all the vertices present in G, then we call it as a spanning subgraph. Okay. So it just spans all the vertices present in G. Okay. And the next important property, if you observe, so let's say we selected these edges A to AB, BE, ED and AD. Okay. So if you observe carefully, so this is what I actually selected is a cycle. Okay. So we have already seen in the previous lecture what is a cycle. Okay. So cycle is just a walk through the vertices and you reach back to the starting vertex again following some edges. Okay. So here the cycle is A, D, E, B, A. So all we want is to select some edges and hold the connectedness property. Okay. So even if one of the edges is not present, even then the connected property holds in a cycle. So it is just like we have a cycle given, and even if we remove one of the edges present, still the connectivity holds. So we don't actually need a cycle in the graph. So even if a cycle is present in the graph, we can actually remove one of the edges from it and still maintain the other properties, and that only decreases the weight of the edges we selected. Okay. So what we want is not to have any cycles. Okay. So, and also we want it to be a connected subgraph finally, because we need a path from any vertex to any other vertex. Okay. So if we recall, any graph which is connected and which does not have any cycles can be called a tree. Okay. And even with these properties, there can be many trees which actually span the whole graph. What we are looking for is the one which minimizes the sum of the weights of the edges selected. So we want to minimize the sum of the edge weights. So we need to select a graph, we need to minimize, and it should span, and it should be a tree. Okay. Now you can see, hence the term minimum spanning tree. So these are some of the observations which we can see from the problem. And now let's design an algorithm, or let's see an existing algorithm for finding a minimum spanning tree of a graph. So there are two main algorithms which are pretty standard in graph theory. So one of them is called the Prim's algorithm, and the other one is Kruskal's algorithm. Okay. So first let's look at the Prim's algorithm. So the algorithm is a greedy algorithm, and it follows it as follows. Okay. So let's start with some vertex. So let's select A. It can be anything. Okay. So we try to slowly expand the tree, starting with this vertex. Okay. So starting with vertex A, so we will add one more vertex to the existing set, and try to make it, and try to expand our tree. Okay. So obviously, so the next vertex to be selected can be anything, so that the edge goes from this set to the set outside. Okay. So to minimize the sum of the weights, so we need to select the minimum of them. So if you proceed a step further into this algorithm, so we start with vertex A and check all the vertices which are going out of the vertex A and with minimum weight. Okay, so we only have the vertex A, the edges AB and AD, and the minimum weight is the edge AD. So we select the edge A to D, and it has weight 5. Okay. So our current tree is having this the vertices A and D and the edge connecting them. Okay. So now we need to add one more vertex to this set, and we need to still hold that connected property and minimize the sum. Okay. So check. So the algorithm is, so maintain the current active tree selected already, and check the edge and select the edge with minimum weight, such that the edge goes from connects a vertex which is already selected and a vertex which is not selected. Okay. So in this case, the vertices A and D are selected already, and so look at all the edges which connect a selected vertex and an unselected vertex. So we have A to B7, and we have D to B9, and we have D to F6. And we have D to E as 15. So among all these edges, we just pick the one with the minimum weight. Okay. So in this case, it is 7. So what we do is, we just take that vertex and expand our our tree which is being formed. Okay. Now our tree that is being formed contains the vertices A, B, D, and these are the edges selected. So now we try to expand one more step again. So on follows. So if you do it quickly, so we want to select an edge which goes out of A, B or D and connect some other vertex which is not selected. Okay. So you can check that the edge DF with weight 6 is the one to be selected next. Okay. So out of all the edges going out of A, B, D and F, you can check that the edge B to E with weight 7 is the one to be selected next. So now out of all the edges going out of this tree being formed, you can check that the edge E to C with weight 5 is the minimum one. Okay. Now out of the edges going out of this, you can check that E to G with weight 9 is a minimum one. Okay. So we have selected all the vertices and the algorithm stops there. So this is the minimum spanning tree for this graph. Okay. So you may ask that if there are more than 2 edges with the same minimum weight, so which one to select? Okay. So the answer is it does not matter which edge you select, because the sum of the weights will be minimum in both the cases. Only the structure of the tree may vary depending on the which edge you select. So this is the Prim's algorithm. So let's do a quick complexity time analysis for this algorithm. So what we are doing is we are maintaining some set of edges at each step, and we are selecting one of these edges with minimum weight, and we are adding this vertex to our set, and we are expanding the set of edges to be considered in the next step. So following the usual notations where n denotes the number of vertices and m denotes the number of edges. Okay. So we maintain a set of edges, and we need to pick the minimum, the one with the minimum weight. Okay. So suppose we have this set. Let's say the weight for this is 10, and weight for this is 2, 3, and weight for this is 4. Okay. So let's name them A, B, and C. So in the current step, we pick the edge with the minimum weight among 3 and 10. Okay. So that is 3. Okay. So after this step, so the vertex C previously had a weight associated with it, the label with that is 10. Okay. But now since B is part of the tree, we need to update the label that is a weight for C. Okay. Because it is connected to the active tree using a edge of a smaller weight than the previous one. Okay. So all that we do is maintain the labels for each of the vertex, which is nothing but the weight associated with it following an edge from active tree to the unselected vertex. Okay. So all we want is a set of n labels, and with the addition of each vertex to the spanning tree, we may change the label associated with that vertex. So we want to update the label, and out of all the labels present for the unselected vertices, we need to pick the minimum one at a step. Okay. So finally we are looking for a data structure where we may update the value of its, we update the keys, and also pick the minimum. Okay, so a binary heap is well suited for this. So this is also at some places referred as the priority queue. Okay. So there are other advanced data structures like Fibonacci heap and other things, but if you restrict the analysis to binary heap, so each of the operation update takes a log n time, and also once you remove the minimum to adjust the heap property, it also takes log n time. Okay. And also if you consider the worst case, so each edge may result in the update of a label for a vertex. Okay. So so how many times in the worst case can we call updates? For each edge there can be one update. So it is for each edge there can be update, plus once you pick the minimum there can be a log n computation to adjust the heap property. Okay. So how many times do we actually pick the minimum? That is nothing but the number of vertices present in the graph. So this is the final complexity for the Prim's algorithm, and if you consider that the number of vertices present is usually in the order of, it's actually less than equal to the order of the edges present, because we are considering the graph as connected already. Okay. So we can actually remove the lower order terms here and simplify it to O of m log n. Okay. So as you can see, this algorithm follows a greedy process. Greedy in the way that we have an active set and we just pick the edge with the minimum weight. Okay. And we are guaranteed that that edge will be part of the minimum spanning tree. Okay. So that's what greedy algorithm tells us. So once you make a local decision currently, okay, so we don't revert back or change the decision again. Okay, so that's what the greedy algorithm tells us. Okay, so the local decisions made at a particular step is not changed again, and that is actually the optimum step globally also. So that's what the Prim's algorithm is about. Now let's quickly see what Kruskal's algorithm is. Okay. So Kruskal's algorithm is more intuitive than the Prim's algorithm. Okay. So what we want to finally is to minimize the sum of the edges selected. Okay. So what can we do about that? So let's pick the edge with the minimum weight and add it to the tree which we want to form. So let's just pick the edge with minimum weight. So there are two such edges, A to D and C to E. So it doesn't matter which one you pick. So A to D has weight 5. So we just pick that. So let's pick the next minimum weight edge. So that is C to E, and which also has weight 5. So that's it. We want to minimize the sum of the weights. So let's keep picking the edge with the minimum weight and add it to the tree which we are being formed. Okay. So but you have to make sure that the properties that there is no cycle and finally it is connected holds. So if you follow further, the edge with the next minimum weight is the edge DF with weight 6. And the next one is let's pick AB with weight 7, and there is one more edge from B to E which also has weight 7. Okay. Now the edges with the next minimum weight, that is 8, is either BC or EF. Okay. So if we consider the edge EF, it forms a cycle with the tree that is already being formed. Okay. So but we do not allow cycles. So we don't pick this edge. Similarly, if we select the edge B to C, it again forms cycle with the already selected edges. So we don't select that. So the next one to follow is 9. Let's take the edge BD. So even now selecting this edge creates cycle. So we don't want cycles in finally. So if you take, there is one more edge with weight 9, that is EG. Okay. So now we have selected all the 7 vertices, and this is our minimum spanning tree. Okay. So the algorithm is very simple. Just keep picking the edges with the minimum weight and add it to the graph as long as the cycles are not formed. Okay. So the only non-trivial step in this is, so how to detect cycles. Okay. So how to pick the next minimum weighted edge. Okay. So these are the only 2 questions which remain. Okay. So we need to pick the next minimum weighted edge. Okay. So the simple solution can be to sort the edges. So that's the pre-computing step which we do. So given the graph, we pick all the edges into a set, and we sort the edges based on the weight in increasing order, and we can just go from left to right in that. So that naturally gives the edge with the next minimum weight. Okay. So on the complexity, if you use any comparison based sorting, is O of n log n, but n is actually the number of edges present, so that is m log m. Okay. So for detecting cycles, so there is a standard algorithm called the disjoint set union, or some people also refer it as the union find algorithm. Okay. So the idea is we keep connecting some disjoint entities, and at any point of time, so if you try to connect 2 entities, so if they are not present in the same set already, so we just connect them. Okay. So if we try to connect some 2 entities, and if they are already connected, then we need to detect that. Okay. So that's what union find tells us. The union is just union the 2 sets, and find is to find if these 2 vertices are already connected by some selected edges. Okay. So we will not go into the detailed analysis of this part. Okay. So usually, so if you treat alpha of n as the time it takes to union the 2 sets or to find if they are connected or not, so how many times do we need to do at max? So that will be equal to the number of edges present. Okay. So for each edge we pick, we actually want to find if the 2 vertices are already connected without this edge. Okay. And there are many algorithms which actually reduces this factor to less than log m. Okay. So this is the main dominant factor in the Kruskal's algorithm. So the complexity for this is O of m log m. Okay. So depending on the value of n and m, you can actually choose which algorithm to pick to give the best performance according to your application. Okay. So finally, if you look at the minimum spanning tree in this case by drawing red edges, so let's follow the Kruskal's algorithm. 5, the next minimum is 6, and the next minimum is 7, and we have one more 7, and joining 8 creates a cycle, so we'll not take this. Joining 8 creates cycle, we will not pick this. Joining 9, we will not pick this, and this. Okay. So if you recall the problem which we defined first, so if the government picks the edges represented in red color, they will be able to connect all the cities. So there is a path from any city, starting from any city to any other city, and also the cost incurred, that is the sum of the weights of the selected edges, is as minimum as possible. Okay. So this is a minimum spanning tree algorithm, and in the next lectures you will see how this concept of minimum spanning tree is used in clustering and other topics.